Welcome to the 8th session of our Chapter 1 Solid State. Today we will discuss about the electrical properties of solids. Solids can be classified into three types based on their conductivities. First one is conductor, insulator, semiconductor. If we want to define the conductor, we know the substance through which the electricity is passing, or then only we can say it is a conductor. And in here, the solids with conductivities ranging between 10 raised to 4 to 10 raised to 7 ohm inverse meter inverse are called conductors. This range you have to remember. The metals are the good conductors of electricity, and they will be having the conductivities in the order of 10 raised to 7 ohm inverse meter inverse. Next one is insulator. The substance through which the electricity doesn't pass through is said to be insulator. And we know the rubber or the plastic are the examples. These are the solids with the log conductivities ranging between 10 raised to minus 20 to 10 raised to minus 10 ohm inverse meter inverse. And the last one is semiconductors. Semi means half. That means half of the electricity is passing through the substance, means we can say it as semiconductor. These are the solids with the conductivities in the intermediate range between 10 raised to minus 6 to 10 raised to 4 ohm inverse meter inverse. Now let's talk about the causes of the conductance in solids. In most of the solids, the conduction takes place due to the migration of electrons when they are coming under the electric field. However, in ionic compounds, it is the ions which is responsible for the conduction due to the movement of ions. In metals, the conductivity depends strongly on the number of valence electrons which are available in the outermost shell. A band is formed due to closeness of molecular orbitals which are formed from atomic orbitals. We learned that atomic orbitals, when two atomic orbitals combine, we are getting two molecular orbitals. It is the bonding molecular orbital and anti-bonding molecular orbital. Now let's talk about the conduction band and the valence band for the conductor, insulator and semiconductor. If this band is partially filled, that is the molecular orbitals we are talking about. If this band is partially filled or it overlaps the higher energy unoccupied conduction band, the electrons can easily flow under the electric field, or they can just move to one another. So it behaves as a conductor. You can see the diagram where the first one is partially filled band, and the second one is, you can see the higher orbital or higher energy level, and it is overlapping the other one. So in this case also, the electrons can just move to the other, or they can just easily pass through. So it is acting as a conductor, or the metals are the good conductors. But if the gap between the valence band and the higher conduction band is large, if the gap is between the valence band and the conduction band is very large, then the electrons can't jump through this, or the electrons cannot jump into the next orbital or next band. So it acts as a insulator. And this one, the gap between the conduction band and the valence band is said to be the forbidden zone. The forbidden zone where the electrons is not at all available. The energy difference or the gap between the valence band and the conduction band is said to be forbidden zone. And the last one, semiconductor, when we are talking about, the gap between the valence band and the conduction band will be small. The gap is not too large. So what happens is, some of the electrons may jump from the valence band to the conduction band, and such a substance shows some conductivity and it behaves as a semiconductor. And semiconductors are very few, so we can use the conduction and the insulator mostly. Electrical conductivity of semiconductors increases with increase in temperature, since the electrons can jump from valence to conduction band. Silicon Silicon and germanium shows this type of behavior and they are said to be intrinsic semiconductors. Now let's talk about doping. It is a process by which the impurity is introduced in semiconductors to enhance their conductivity. I'll repeat, it is the process by which an impurity is introduced in semiconductor to enhance their conductivity. And after doping, we can have two types of semiconductors, N-type semiconductor and P-type semiconductor. The first one is N-type semiconductor, or the other name of that one is electron-rich impurity. In the word itself, we can understand that this semiconductor is having some electrons extra, which is acting as the impurity there. Now we have taken an example of silicon, or we can take instead of silicon germanium, which belongs to the 14th group of the periodic table. So they will be having how many valence electrons? They will be having 4 valence electrons. And in their crystal, each atom forms 4 covalent bonds with their neighbors. Because if you are taking a full crystal of silicon or germanium, each atom is having 4 valence electrons. So the other silicon will be having the 4 electrons. The next to the that silicon, again silicon atom we are keeping, it is having again 4 valence electrons, and they will be sharing the electrons with each other, forming 4 covalent bonds. Now in this, if we are introducing an impurity, then the process is said to be doping, and it should increase the conductivity also. So when we are doping, or when this 14th group elements are doped with 15th group element like phosphorus or arsenic, if 15th group we are having, that means they will be having the valence electrons 5. They occupy the lattice sites in silicon or germanium. What happens is 4 out of 5 electrons are used in the formation of 4 covalent bonds with the neighboring silicon atom. But what about the 5th electron in the phosphorus or arsenic? It is extra and it becomes delocalized. In this structure, you can see other than all, the silicon atoms are covalently bonded with 4 covalent bonds. Each silicon is forming 4 covalent bonds. Now in this, if a phosphorus is introduced, it is having how many electrons? 5 valence electron. 4 will be used up making the covalent bonds. But the 5th electron is extra here. This electron is delocalized, and this extra electron is increasing the conductivity of this semiconductor. So these delocalized electrons increase the conductivity of doped silicon or germanium. Here, the increase in conductivity is due to the negatively charged electron, and hence the silicon doped with electron-rich impurity is named as N-type semiconductor. The second type of semiconductor is P-type semiconductor, or we can name it as electron deficit impurities. That means electron is less here. Silicon or germanium we are taking as a semiconductor can also be doped with the group 13 element like boron, aluminium or gallium, which contains only 3 valence electrons. The place where the 4th electron is missing is called the electron hole or the electron vacancy. Now you can see the diagram. All the silicon atoms are arranged where the covalent bonds are formed. But what about this place where the boron is introduced? Boron is having only 3 valence electrons. So out of these 4 covalent bonds, only 3 it could make. The one it is not having any bond. Why? Because there no electron is there. So how can it be a bond? So here an empty space is there, or the electron is missing, which is said to be the electron hole or electron vacancy. An electron from a neighboring atom can come and fill the electron hole. But what happens in doing so? It would leave an electron hole at its original position. So it is not at all possible. This hole moves through the crystal like a positive charge, giving rise to electrical conductivity. So in N type, the extra electron was there, and in P type, the hole is there, or the electron deficiency is there, and it rises to electrical conductivity. This type of semiconductors are said to be P-type semiconductors. Next is the applications of the N and P-type semiconductors. And the combinations of N and P-type semiconductors are used for making electronic components. Diode is a combination of N and P-type semiconductors, and it is used as a rectifier. Transistors are made by sandwiching a layer of one type of semiconductor between two layers of the other type of semiconductor. The examples are NPN and PNP type of transistors, which are used to detect or amplify radio or audio signals. The solar cell is an efficient photodiode used for the conversion of light energy into electrical energy. So these are some of the applications of these type of semiconductors. Next, we have to discuss the magnetic properties of solids. Every substance has some magnetic properties associated with it. The origin of these properties lies in the electrons, and each electron in an atom behaves like a tiny magnet. Its magnetic moment originates from two types of motion. One is its orbital motion around the nucleus, and the other one is its spin around its own axis. So electron is having two spins, that is one about its own axis and the other one is around the nucleus, the orbital motion it has. So its magnetic moment originates from these type of motions, and each electron has a permanent spin. Each electron has a permanent spin and an orbital magnetic moment associated with it. And the magnetic moment we are measuring with which unit? Bohr magneton, and it is represented like this: mu b, Bohr magneton, and it is equal to 9.27 into 10 raised to minus 24 Armstrong meter square. On the basis of their magnetic properties, the substances can be classified into 5 categories. First one is paramagnetic, second diamagnetic, third ferromagnetic, fourth antiferromagnetic, and the fifth one is ferrimagnetic substances. So based on their magnetic properties, the substances or the solids can be classified into 5 categories: paramagnetic, diamagnetic, ferromagnetic, antiferromagnetic, and ferrimagnetic. We'll talk about paramagnetism. These are the substances which are weakly attracted by a magnetic field. They are magnetized in a magnetic field in the same direction. They lost their magnetism in the absence of magnetic field, and it is due to the presence of one or more unpaired electrons which are attracted by the magnetic field. And same sentence we have learned in coordination compounds. There we are learning in the orbitals or atomic orbitals, if unpaired electrons are there, it behaves as paramagnetic in nature. The same sentence is here. It is due to the presence of one or more unpaired electrons. And the examples for this are O2 plus, Cu2 plus, Fe3 plus, Cr3 plus. Next is diamagnetism. These are substances which are weakly repelled by a magnetic field, and they are weakly magnetized in a magnetic field in the opposite direction. And it is shown by the substances in which all the electrons are paired and there are no unpaired electrons. The first sentence itself is enough, that is, the electron should be paired. If it is paired, then we can say the substance is diamagnetic. Pairing of electrons cancel their magnetic moments and they lose their magnetic character. And the example for these are H2O, C6H6, NaCl. Third one is ferromagnetism. A few substances like iron, cobalt, nickel, gadolinium, and CrO2 are attracted very strongly by a magnetic field, and these substances are said to be ferromagnetic substances. Besides strong attractions, these substances can be permanently magnetized. In solid state, the metal ions of ferromagnetic substance are grouped together into small regions called domains. Thus, each domain acts as a tiny magnet. In an unmagnetized piece of ferromagnetic substance, the domains are randomly oriented and their magnetic moments get cancelled. When the substance is placed in a magnetic field, all the domains get oriented in the direction of the magnetic field and a strong magnetic effect is produced. This ordering of domains persists even when the magnetic field is removed and the ferromagnetic substance becomes a permanent magnet. So there's an alignment to show the ferromagnetism where all the domains will be parallel to the magnetic field. So it will be in a orderly manner. Fourth one is antiferromagnetism. These substances have domain structure similar to ferromagnetic substance, but their domains are oppositely oriented and cancel out each other's magnetic moment. This is the difference between ferromagnetic and antiferromagnetism. The example is MnO. Next is ferrimagnetism. It is observed when the magnetic moments of the domains in the substance are aligned in parallel and anti-parallel directions in unequal numbers. The arrangement is not regular and they are weakly attracted by the magnetic field as compared to the ferromagnetic substance. These substances also lose ferrimagnetism on heating and become paramagnetic. Fe3O4 magnetite and ferrites like MgFe2O4 and ZnFe2O4 are the examples of such substance, that is ferrimagnetism they show. And the alignment can be explained through this diagram. The first diagram, you can see the domains are in the parallel position. All the domains are in upward direction, so it is ferromagnetic in nature. The second one we have said the domains will be alternately arranged. That is, one will be up, the second one will be down, like that. Parallel and anti-parallel you can see. That is anti-ferromagnetic. But the third one, ferrimagnetic, is parallel and anti-parallel domains can be seen, but it is in unequal way. Here you can see two are upward, one is down, again two upward, down, like that. So there is no proper arrangement for the domains in the structure. So this is how the magnetic behavior we are explaining. Thank you. With this, we are finishing our first chapter.